Okay, so hi everybody. My name is
Hello,
Patricio.
hello, Patricio. Hello, Patricio. So hello, everybody. Welcome to our machine learning seminar. And today we'll have a pleasure to have a presentation from Patricio Peralta-Braz from the School of Civil Engineering and Environmental Engineering of the University of New South Wales in Sydney, Australia. The title is already visible on the screen. So Patricio, please go ahead. The virtual floor is yours.
Okay, thank you for the introduction. Thanks for the invitations. I'm very happy to be here and present part of my project. And this is a project in collaboration with the Dr. Elena Strochenko, the Dr. Mary Mikey Almendradi, and the Dr. Makbuk Hassan. The name of the presentation is Joint Optimization of Energy Harvesting and Sensing of Piezoelectric Energy Harvesters in a Cable State Spring based on a deep learning framework. Okay, so rings are crucial element in transportation systems due to the higher cost, the connectivity that they add to the network, and the several consequences of their collapse. For that reason, structural health monitoring systems are installed in their structures in order to ensure their safety. In some contexts, the best option is the use of wireless devices in order to monitoring their structures, which commonly are supplied by chemical batteries. However, the use of battery requires the periodic replacement of them, a process that can be difficult, expensive, or infeasible. In that sense, one attractive alternative that has arisen in the last year is the use of energy harvesting. In particular, the vibrational energy harvesting has a big potential in this particular context because they can transform the traffic-induced vibrations into electrical power. There are different systems, but one of the most popular is the piezoelectric energy harvester, due to its higher efficiency per unit of area. This is its typical configuration, which consists in one or two piezoelectric layers joined to a substructure. The device is installed in the vibration source. So in that case, the idea is to install the device under the desk of the bridge. And this one is convenient for the installation process and also because provides some protection of the weather conditions. There are some studies that have been addressed the use of this technology on bridge. In general, the conclusion is the same. It is possible to use this device for continuous or in some case intermittent measured operations. However, the use has not become so popular if we compare with other technologies due to the order of power that they produce. So in order to address this problem, we have we can address this problem from two points of view. We can increase the power generation of this device, or we can reduce the power consumption of this one. So putting our focus in the second alternative, we propose to use this device as a sensor and energy harvesters at the same time. So this offers a new design space because they have the opportunity to be more efficient than traditional sensors because they doesn't require a power supply for their operations. In the literature, there are some research that show that it's possible to use this device in order to use this device as a sensor in order to determine the accelerations from some vibration source or in order to identify the scour on print. However, in this study, we are interested in a different task. We are interested in the traffic characterizations on the print. Traffic characterization is an essential task in transportation system because it provides reliable data for management and making decisions in different tasks such as traffic monitoring or pavement evaluation. There are many sensors alternatives in order to perform this task. However, we propose to use the voltage generated by these piezoelectric devices in order to identify the characteristic of the traffic using some deep learning techniques, okay? So the deep learning have been using in this context using the signal from strange and acceleration sensors in order to infer some of these characteristics. So we think that it's possible to extend some of these framework for our specific case. Okay, in our work, we are going to focus in this particular cable stage range, which is located in the state of New South Wales in Australia. The ring has one traffic line and one pedestrian line. And under the ring, there are a set of accelerometers and strain sensors. So in particular, we are going to use one device that is installed near to the center of the bridge. And also we are going to use two pairs of strain sensors in order to determine the speed of the vehicle that passed over the bridge. In other hand, we have one numerical model in order to estimate the voltage generated by any geometry of piezoelectric energy harvesters. This model is based on the Hamilton principle. We use these particular constituted equations. And also we assume that the device is an Kirchhoff plate, and we use isogeometric analysis in order to solve this problem. Okay, so this is the main idea of the first part of the framework. The idea is to use the acceleration signal from one of the sensors installed on the bridge. Later, using our numerical method, estimate the voltage generated by one piezoelectric energy harvesters. Next, using one time frequency analysis method, obtain image like this in order to use as an input in our neuronal network. The method that we are using here is the continuous wavelet transform. On the other hand, we are going to use pairs of strain sensors in order to calculate the speed of the car that passed over the bridge, and use this information as the labels of our image. So we build a database. We divide this database and we training and testing our model in order to obtain some accuracy of the speed of the car that is passing over the bridge. Okay, so related to the selection of the convolutional neural network, it's important to note that the architecture is something that varies depending the specific requirement of our task. So it's a good idea to evaluate different architecture before to design the final model. So in our case, we evaluate several popular architectures of neuronal network, such as GoogleNet, BGG, ResNet, and a couple more. And we conclude that the best one in our context, it was AlexNet. So AlexNet is one of the most effective convolutional neuronal network, and this is their architecture. And the architecture has 8 sliders. The first one are convolutional sliders, and the 3 last are fully connected sliders. In addition, in the training process, we use transfer learning because this makes more efficient this process. Here, the idea is to train the neuronal network using natural object image. Next, we replicate the first sliders, the convolutional neural sliders, which are the responsible to extract the information from the image. And then we just retrain the last slider using one small data of our digital image, or the CWT image. Okay, so I'm going to present our study case. And here we consider more than 1,000 events. In addition, we consider 3 labels related to the speed of the car that passed over the bridge, and we train in the model several times in order to obtain some average accuracy of our model. The accuracy that we obtain from one particular geometry is around 90%. But one question that arises here is, what is the impact of the geometry of the piezoelectric energy harvesting in the sensing accuracy of our network? So in order to address these issues, we consider in 6 devices which only differ in the length of the devices, that is to say, in this distance. The rest of the geometrical properties is the same. The mechanical properties are also the same. And the length that we're considering is 5, 10, 15, 20, 25, and 30 centimeters. So the neuronal network is training multiple times, in particular 50 times for each case, and here I present the result. So in the axis Y, I have the accuracy of the neuronal network. In the x-axis, I have the length of the device. So we can see that the network accuracy vary with the length of the device, reaching the highest value when the length of the device is equal to 25 centimeters. So to interpret this result, it's necessary to consider that the convolutional neuronal network extracts information from the time frequency analysis image. So here I present the 6 image from the 6 device that we are studying from one particular event. That is to say, when a specific car passed over the bridge. The pink dotted line represents the resonant frequency of our device. So if we pay attention, we can see that the higher contrast in the wavelet coefficient or in the image color of the figure is around to some of the resonance frequency of our device. So that means that the information provided by each device differ between them, and some of them is better than others in terms of the predictions that we can do from them. And this leads to different sensing performance between them. Okay, so a new question that arrived from here is how the sensing performance and the energy harvestings are related between them. So, so in order to address this problem, sorry, I made a mistake in this slide, but in order to address this problem, we are going to use 5 different continuous time windows accelerations. We are going to estimate which is the average energy that we can harvest from the fringe from each device, and we are going to compare the result. So in the axis Y, we have the accuracy of the network, and in the x-axis, we have the harvested energy from each axis. So from here we can see that the optimal device in terms of sensing is the device that has an length equal to 25 centimeters. But in the other hand, the optimal device in terms of energy is the device that has a length equal to 15 centimeters. That means that there are like a trade-off between the sensing accuracy and the energy harvesting of our device. So if we want to increase one of the objectives, it will be necessary to decrease the other one. So based on this result, it's possible to state that the design of a bifunctional piezoelectric device is not a trivial task, because no single configurations simultaneously maximize both. So in this regard, a multi-objective optimization framework is proposed to effectively tackle the selection of the geometry to address this trade-off between the energy harvesting and sensing. So here we have like the proper mathematical formulation of our problem. The idea is to maximize both at the same time, taking in consideration different geometries. In particular, we are going to use one genetic algorithms in order to solve this problem due to its good Pareto-Fromm convergence. One of the main challenges of this present optimization problem is the long computational times to estimate the sensing accuracy and also the energy harvesting performance from one single device. So one attractive options in order to address this problem is the surrogate modeling techniques. The surrogate model consists in one approximation in the relationship between the input and the output of a system using only one limited number of sampling from a high fidelity model. In particular, we are going to use a Kriging model due to its ability to indicate the level of prediction of the confidence of one new sample, and also due to its good performance with a reduced number of sample points. Okay, so here I have the result from our optimization problem for 3 different design space. Okay, so here, so the result that we are going to obtain, it will be not just a single design, it will be a set of geometry where each of them, it will be better in one of the objective functions, in one of them. So for example, this geometry is better in terms of energy than the rest of the case, but is worse in terms of sensing accuracy. So at the end, it will be the designer, the people who is going to take the decision, and which of this geometry is going to choose based on the limitation of their particular case, or yeah, basically based on the limitation of their particular application. Okay, so basically, okay, so some challenges and future work. One of the things that we are working right now is to improve a little bit the resolution of our predictions, because right now the resolution of the speed that we obtain is so big. In addition, we are interested in to extend our methodology in order to identify the weight of the vehicle that passed over the bridge. And also we are trying to find some options in order to reduce the variability in our predictions and also to reduce the computational time of each sample. Okay. Okay, thank you for your attention. This was part of my research project. Thank you so much.
Thank you, Patricio. So let's open the discussion. As usually, I have some questions, but if any of you has any question, just raise your hand or switch your microphone and ask question. So maybe
I would have a question.
Andreas.
Let me start. Yeah, okay. Yeah, thank you very much for your nice presentation. Did I understand correctly that you kind of make a detour via these time frequency images in order to facilitate the whole process? So you generate out of available digital data these images, and then you go through the learning process. Is that by intention, because you would like to take advantage of some sort of filtering that you get by generating those images, or is it simply because all these learning methodologies are available for images? Because I could imagine that you could also directly start from the digital data that you have available, because going via images raises the question how transferable the methodology is, because encoded in those images are like ranges of data, right? So so is that by intention, or is that just because the learning models and these networks are set up for images and directly available?
Actually, we are starting from other framework that is proposed by other researchers, that they use the acceleration signal in order to make the prediction of the speed and the weight of the vehicle. So we started this one like our benchmark problem, and then we try to extend this problem for our problem, that is the case of the piezoelectric device. But right now we are open to explore different alternatives. I don't know, we are just starting with this research area. So yeah, maybe in the future we can explore using just directly the data that we have, or I don't know.
But for now, having those image-based methodologies in place and all these network architectures that provably work for those images, that's a convenience approach. That's my understanding, right? Oh, yeah.
Yeah. Because
Oh,
I think that the accuracy that we are obtaining is good, you know. It's around 90%. In some reference paper, it's even higher. So I think that, yeah.
Yeah, just for me to understand your approach and the setting more specifically. Okay, thank you.
Thank you.
So I can see that Elena has posted in the chat the link to the paper, probably with more details about the methodology. May I have a question, taking the opportunity that no one else yet raised a hand, which is again related to what Andreas mentioned, meaning the very question about the use of the images in the context of convolutional neural networks, because convolutional neural networks are a natural choice for the images. They are capable of spotting some local features and combining those features geometrically using the fact that you have a grid data structure in the form of the image. However, in your case, the image is very specific because it is derived from the frequency domain, and you filter it and compose an image in which you have a time dimension in one coordinate and the frequency dimension in the other coordinate. So it is a very specific image. It is not a real life natural image, but a very specific one. And then let's say the question, let's say the correlation in time is to some extent obvious, that you have some events that are closely correlated, which are that are, let's say, closer to one another in time. But the question is, what about the correlation in the frequency domain? They can be quite far from one another. There can be no very obvious pattern or local pattern that can be promised there. So my question is, so why CNN architectures here? I mean, you showed that it has proven to be efficient, or the accuracy is quite high, but do you have some insight, some intuition why it can be advantageous, or why it would work at all, the approach of convolutional neural network? Did you have any thoughts on that, or you can provide us with some thoughts on that?
Okay. You say which are the problems that we have right now with the convolutional neural network?
So, I mean, the neural network architecture is somehow usually adapted to the problem at hand, right? So the CNNs, the convolutional neural networks, are good for images. But in your case, you don't have a standard image like your handwriting or some picture of somebody, but some filtered image. I mean, you have the data, which is the frequency of your vibrational frequency, and then you transform it into the image. And the question is why the CNN can work for this sort of images.
Okay. Because at the end, the image that we are using is like a representation of the reaction or the interactions between the vehicle and the range. So I think that when the speed of the vehicle change, the way that the range is going to respond, it will be different between the three labels that we are considering right now. So this one is going to activate some different vibration mode in the range. So this vibration mode is going to we are going to recognize in the different frequency in our image. So maybe from some specific range of frequency, the colors, it will be in some specific positions, but for other difference speed, it will be in another difference position. And so right now it's working good because the range that we are using is wide, but maybe if we want to reduce the resolution to, I don't know, only 1 meter per second or 1 kilometers per hour, convolutional neural network is not going to work so good. I don't know. This is one thing. Other thing is also the number of samples that we are using right now. Right now it's not too much because we are using on-field data. So I don't know, we are thinking into use maybe samples from some numerical method, or I don't know. We are exploring alternatives. But right now, in this condition, it's working.
I see. Thank you. I can see that Stefan has his mic on. Stefan, do you want to comment on something or ask question?
Yeah, sorry, I put the video on also. Maybe that's useful. Can you hear something? Not too much echo?
It's fine.
Okay, super nice. And no, not technical question, but practical question. Did you think how easy is it to make this happen in real life?
So in real life, the idea it will be to install directly the device in the brain. Right now, this one is like a proof of context more than go to the real application because, for example, we are not considering if there are 2 cars in the range at the same time. So this one is like a big simplification. And so yes, I think that right now we are not ready for the real life, but we go in that direction at least.
And could you imagine an experiment in the lab that could help you get closer to real life?
Yeah, of course. Actually, maybe I forget to present this one because we have some experimental setup. We have like a shaker that can replicate the vibration of the ring. So the idea is to replicate the vibration of the ring, design some piezoelectric energy harvesters, and make the test here in order to see if the voltage that we obtain from different type of event can be produce good predictions using this framework. But yeah, this is our idea right now.
And in terms of the practical achievability of this, in terms of materials to transfer, the conversion rate of energy in what you basically harvest and you use to sense, right? I mean, that's at least one of the ideas. And then, so you have the harvester becomes the sort of battery for the sensor and so on. But is it something that's science fiction, or is it possible using existing materials, or do you need to come up with new materials, or new setups of materials, or new combinations of materials? Or is it like doable today, now, immediately, or is there some limitations in achievability from that point of view?
Yeah, right now we are thinking everything using the current materials, the materials that there are available right now. In terms of energy, I think that we are not producing too much energy in our specific applications due to the characteristic of the range that we are using because it's small, the traffic is not so heavy. So yeah, this is one limitation. Also, we are exploring the use of meta materials in the case of the piezoelectric energy harvesters, because they give us more options in order to design devices that produce more information from one single event. And also to increase the power generation because we can produce some local resonance, and this one has the potential to increase the power generation. Yeah.
Sorry, I just want to jump in.
Yes, please go ahead, Elena.
Yeah, I just wanted to comment for Stefan that the whole idea here is not to have an energy harvester which will power a sensor. The idea is not to have a sensor, but to have one single hardware which can be used for energy production, and then that energy that you produce, you can utilize to power other parts of the system more efficiently because you don't have a sensor, right? But you use the voltage produced by the harvester, you use it for sensing. So this concept is called simultaneous energy harvesting and sensing. That's why we are optimizing for two objectives and not only the energy production.
Sorry for getting it wrong.
Maybe I have a follow-up question on this, because the signal that you assume is dominating the response of the bridge, and therefore the energy produced by the harvester is the traffic. But there are
not
other...
necessarily, actually. That's a good point. Yeah, because we did a lot of study on shape optimization just for energy production. And it turned out that we are producing a lot of energy just from ambient vibration for this particular bridge without any traffic. Mm-hmm. So it's not necessarily from traffic.
Okay. And for how long would you like to install such energy harvesting devices? Because if they are operating for a couple of years, I guess, then fatigue behavior could be a problem. No or yes?
we haven't looked that far.
I saw that one of the lengths studied was like 30 centimeters, which is rather long, I would say.
It's this particular bridge which has very low natural frequency, something like 2 Hertz. That's why we have to deal with very large devices.
Mm-hmm. Yeah. And the deflections, of what size would be the tip deflections of these harvesters then? Because if the excitation signal is like in the low Hertz regime, then the response would be low frequency, probably. So if the length of that cantilever thing is 30 centimeters, what would be the tip displacement?
I don't know, Patricio, can you comment on that?
No, really, I don't have the number in mind right now. Yeah, I don't know.
Yeah, another thing is that we are using a linear model here, which is also may not be suitable, but now we are extending to non-linear, and we also running a lot of experiments to find the damping parameters. And we are also extending to metamaterials with the idea to record different voltage signals from different parts of that plate and explore how that can be used for sensing. And maybe in this case, we are back to the use of images. Maybe using the images will not be optimal in that case anymore. Mm-hmm. Mm-hmm. Well, it's not optimal now, but it may be even worse.
Okay.
Yeah, so that's the plan.
Okay, thanks.
Okay, thanks. So may I let's say, go back to our comfort zone and ask a question about this machine learning part again, because there was something that puzzled me a bit, and I'm trying to find an answer myself about this transfer learning part that you mentioned. In particular, if I understood correctly, you have your convolutional neural network, and you have some sort of coarse-grained network that is being trained on some standard images, not the frequency, like a filtered frequency into the image, but like some images from the real life. And this was used for the pre-training the network, right? And then transferred to as a initial guess for your training. Is it correct, or I missed something? And why it would work?
Yes, but basically this is the idea. We use ImageNet, that is like a huge database of real image, in order to train the neuronal network. and then we transfer all the value of the coefficient of the convolutional neural network, and we just retrain the last sliders, that is the fully connected sliders, using the database that we have from the bridge. Yeah.
Okay, so you use the first part of the neural network of this AlexNet as a filter, right? Which is trained on the standard images.
Yes, in order to extract some feature from the image. Yeah.
And then you use a fully connected network to do the rest of the job.
Yeah.
I see. Okay. That's clear. I'm quite surprised that one can connect the real life images with these frequency domain images, which doesn't need to be super correlated one to another, right? One is a kind of technical plot and image, and the other one is a natural image, which both of them don't need to have too much correlation in between. But okay, it seems that in this particular case it is working. That's quite interesting. All right, I cannot see any more question or comment. I can also see the comment of Sahar, who also confirms that she uses also CNNs for time series, right, Sahar? So that's just a comment from the previous question. All right, thank you so much for your presentation, Patricio, and thank you for the discussion and your attention. I will keep you posted about the future seminars, and have a good evening for the people in Australia, and good day for other people who are in different time zones. Bye-bye.
Thank you.
Thank you for the invitation.
Thank you. Bye.
Bye.